Okay, hi everyone. Sorry for the delay. I'm just having some technical problems here. I need to get some files to show. Somehow it's not allowing me to do what I need to do, so I'm going to have to take a photo with my phone. Oh, I see. Okay. Sorry about that. All right, so I just need to clear up a few things about the hydrogen atom. And also, I put the remaining assignments on the Slack. So basically, I'm trying to cover in the remaining few classes that we have. I'm trying to cover three important ideas. The first is this one, which is the hydrogen atom, which basically dictates the structure of the periodic table and most of chemistry. The second is the Wigner classification of particles, which is the fundamental result that classifies all elementary particles of physics. And the last is perturbation theory and Feynman diagrams. Some would say that one should not include all those topics in one class, never mind just a few days, but I don't care. Yeah. I figure that you should be exposed to the most important ideas, not just the ones that you can understand. That's a joke, by the way. You can understand these three ideas. They're actually not that complicated. Okay, so the first thing that I want to say is that so I didn't go through the detailed derivation for how you solve this equation. This was the see basically the hydrogen atom, it breaks up as two systems. One is a free particle on the sphere, and that is relatively easy to solve. And I gave the explanation for how you explicitly solve and decompose L2 of the S2 to get your spherical harmonics, which are eigenstates of various energy. And that is that is a very nice and clean and nice result. But there's also this radial aspect, and the way that the particle, the way that the electron behaves in the radial fashion, that's controlled by this ordinary differential equation in one variable. So this is something that you would have studied in ODE class, and I just stated the result. So what I said was that in order to find a solution that is useful to us, we need for the solution multiplied by r, the coordinate function on this r plus, that this should be an L2. So this means that it doesn't necessarily that this r function, when we're solving this equation, we might find solutions for various different values of E, for which the behavior of r at infinity is such that it doesn't decay fast enough, and as a result, r multiplied by this will not be an L2. If you try to integrate it, it will have have an infinite integral. Okay. And so what that means is that it's not an element in the space, and that means we're not getting an eigenstate inside the Hilbert space. Okay, but okay, now okay, and when we restrict our attention to finding those eigenstates with this L2 property, we end up finding eigenvalues which are like this, 1 over n squared. Okay, and this is a really important prediction of quantum mechanics. Okay, because what it's saying is that even if we assume that the angular momentum, even if we assume that the L parameter is 0, and we have these spherically symmetric eigenstates for the hydrogen, it can have various energy levels, this one, and this one. And as you can see, they're accumulating towards 0, and they behave like 1 over n squared. Okay, and so what that means is that what that means is that the electron might be in such a state, and it might okay, so I'm going to say something which is going to turn out to be false, but I'll correct it later. Okay, but it's just because I don't want to confuse the idea. The basic idea is correct, which is that you could imagine that the electron is in one of these states, and that it decays to a lower energy state, right? You could imagine that it goes down to this state. Now, why would it do that? Well, the only reason that it would change its energy level is if it was interacting with some external force, or if it was interacting with something. And electrons, because they are charged, that means that they couple to the electromagnetic force, and so it could release light. It could release a photon. Okay, and if it does release a photon, and if it goes down one energy level, then the energy of that photon would be fixed. So, and that fixed energy level would be the energy that would go into the photon would be the difference of the energy levels here. Okay, and so when you draw the experimental spectrum of hydrogen, say one way to do it would be to shine light on hydrogen and then energize all the electrons, so they're all getting very high energy states randomly, and then you just stop lighting it up, and then you just wait with a very sensitive color meter and see what color sparks come out of the electron, come out of the hydrogen atom. And these would occur at certain bands, certain frequencies. Okay, and let me just show you what it looks like. Okay, sorry. It's very sensitive. You can see that. So you see that that you could have many different decays, and depending on where it decays to, this is the zero energy level here, and here we have the accumulating energy levels, and depending on whether it drops down to the bottom or drops to the second or the third, right? It will give a series of different possible wavelengths. Okay, so the wavelengths. So the way that they label them, like Lyman, for example, is that it's about where they go to. If they go all the way down to the base energy level, then we're going to get a sequence of frequencies, energy levels, which are like these energy levels here. And so it's an infinite series. And this infinite series is like, in terms of the energy, remember that the energy is like some constant times 1 over n squared. So this would be like, this energy would be 1 over 4, or 1 over 1 minus 1 over 4. So that would be 0.75 times some universal constant. Okay, this one here would be 1 over 1 minus 1 over 9, and so on. So we get larger and larger energy levels, which all have the form, 1 over 1 minus 1 over n squared. So it's a difference of inverse squares. Okay, and the people who studied the spectrum in the spectrometer, of hydrogen gas, which is all around the universe. So you see these lines whenever you look at stars. They noticed this fact. They actually noticed this before the advent of quantum mechanics, that the energy levels of the bands of the spectra, they are energy levels given by a difference of inverse squares. So they already had that information. So imagine the person who came up with a solution to this ODE for the first time and saw that the energy levels were inverse squares. It's a kind of remarkable discovery. And then and then of course, if it goes down to the second, then we get another infinite sequence. So we have an infinite series of infinite series, an infinite sequence of infinite sequences of possible energy levels, all quantized for the energy levels of hydrogen, for the spectrum of hydrogen. Okay, now, okay, so that's the first thing. Now, in something which I just said is a lie, and the reason that it's a lie is that yeah, the reason that it's a lie is that it turns out that you cannot drop from this energy. Oh, you can't see what I'm writing. Sorry. It turns out that you cannot drop from here to here. That's not possible. It turns out that you can only drop from here to here. Okay? Or from here to here, or from here to here, or here. Okay? Why? Why is this? So this is called a selection rule. So some remarks. That's what I'm doing today, is making a bunch of remarks to teach you how this thing is applied in chemistry. So first of all, the energies are proportional to 1 over n squared. So this tells us that the spectrum of hydrogen, let's say the emission spectrum. Emission spectrum means the frequencies of light that hydrogen is able to emit. That's the emission spectrum. Consists of difference of inverse squares. Okay, and depending on the value of n, for each n, there is a series indexed by m. Okay, and these are all experimentally observable. Okay, number 2, not all decays are possible. Okay, due to what are called selection rules. Okay, and this is one of the great successes of representation theory. So what do I mean by this? So let me just get this right. Okay, so suppose that, let me just explain this, this fact. So suppose the electron is in a state in, let's see, what did we call these? Inside the L eigenspace. You see how we indexed SPDF? That's indexed by L, the value of the angular momentum highest weight. So let's say it's in VL, the highest weight L. So this means that it's the 2L plus 1 dimensional representation of SO3. Okay, so let's say it's in that state, one of those states. Now there's many degenerate states. Like I explained before, if it was L equals 1, right, then like for example, in this particular state, there would be 3, because this is a 3-dimensional all of these lines and all of these energy levels, they form irreducible representations of dimension 3, highest weight L equals 1. Okay, so then what's going to happen to it? Well, it's going to either emit a photon or it will absorb a photon. And the way that it can do this is that there must be some interaction term in the Hamiltonian, which allows the electron system and the photon system to interact. Okay, so it's tricky to give a full treatment, mathematical treatment of this, but you have to think that basically the photon is in some state. It's in some vector space of states. That vector space of states is, what is it? So this emission or absorption involves an interaction between the photon, which has a state in V1, the vector representation. So the photon is a spin 1 particle, and it behaves under rotation like a vector. Maybe it's not so surprising since it points in a particular direction in R3, but it has a state in V1, the vector representation of SO3. And it's an interaction between the photon and the electron. Okay, and so that means that that when the photon and when the photon is coming, just imagine that the photon is really close to the electron. Okay, so then you have two quantum systems. You have the electron and the photon. So before emission, or let's say before absorption, we have the electron. After, we have the electron and some photon. Okay, maybe the photon has a different color. Okay, and so this thing is in some state, is in L2 R3 C, the wave function of this electron, and this one is really actually, I'm just trying not to make it too complicated. So what I'm trying to say is that there's a pair of particles, and so therefore you have two systems, and so you have to tensor them together, right? So this is in the V1 representation, and let's suppose that this is in the VL representation. Then this joint system would be in the V1 tensor VL representation. Okay, now if you use the Clebsch-Gordon decomposition, right, then what do we have? Well, we have V1 looks like this, and VL has some, highest weight L. And when we tensor them together, we get this rectangle, and then we're supposed to sum up along the diagonals, right? And so what you'll see is that this V1 tensor VL is the sum of, well, so the highest weight, let me draw it here. So this is going to be 0. Whereas this one will appear twice, this one will appear twice, this one will appear 3 times, and notice that it's 3 is the maximum. Oh, I'm sorry. Okay, because the thickness of this is 3, because this is V1, right? then when we cut by a diagonal, the maximum number is 3. Okay, so this will be V L plus 1. That takes care of this one. So this generates VL plus 1. Then here, there's another highest weight, which is lurking there. So that's VL. And then here, there would be the third one, VL minus 1. Okay, and so what this is showing us is that when the resulting state, this state here, must be in a linear combination of these 3 states. Okay, so this is basically saying that that if you have a state here somewhere, and if it decays, it can only decay to here, here, or here. It cannot decay 2 over. It can't go from P to F. It has to go from S to P, or from P to S, or D, or maybe to P itself, right? So it can only either stay within its own column or move to the next neighboring columns. That's what this result tells us. So the selection rule is that the electron can only move from an orbital to adjacent orbitals, or to its own orbital. Okay, but actually this one, there's another selection rule, which I'm about to say, which excludes being sent to itself. Okay, and okay, and this one is quite interesting. I just want to make sure that I stated correctly. So this is basically, there's a more fundamental reason why this is happening. So the reason why this middle one is excluded, okay, it's because of the fact that the photon is massless. The photon is massless, and so although it behaves like a vector, it cannot be at rest. So the angular momentum actually has to be, it has to be either this or this. It cannot be the one in the middle. That's the essential reason. But let me give a kind of direct explanation for it. So there's another selection rule. So the potential function, this is spherically symmetric. And is invariant under x, y, z sent to minus x, minus y, minus z. Okay, and this is a transformation of 3-dimensional space, which is called the parity transformation. It's a really famous transformation because everyone thought for many years that our universe, the physics of our universe, is invariant under this parity transformation. but it turns out not to be. That was discovered in the 50s and 60s, but to a great approximation, it is. This is not obtainable by a rotation. So this is an orthogonal transformation which changes the orientation. But for this physics, for this problem, it's definitely invariant under this, and so that means that that this defines an action. This defines a symmetry group Z mod 2Z. It's just the group plus minus 1. So it's a simple group of two elements. And this acts on the Hilbert space. And so everything decomposes in terms of a representation of this group as well as the SO3. So it's not just SO3 that's acting on these vector spaces. It's also this Z mod 2Z, which is acting. Okay. And now we come to this fact that we studied before, which is that the fundamental the kind of fundamental difference between all SU2 representations and SO3. The SO3 ones are even dimensional. No, I'm sorry. The SO3 ones are odd dimensional and have even highest weight. Okay, and they correspond to let's just see here. To these spherical harmonics, like where are we? Oh yeah, here they are. Yeah. And if you see how this thing looks, the parity transformation, what does it do? It sends theta to pi minus theta, and this function is independent of that. And it sends phi to phi plus phi plus plus pi. Yeah, here, that's how they all behave. So that's right. And so for some reason I tried to simplify this, but I'm not seeing. Phi. So theta goes to, no, I think that's right. Theta goes to pi minus theta. sorry, I was just trying to argue that these representations are even, or in other words, when you act by this reversal, the orbital is unchanged. So the action of the Z2 on these representations, the ones that occur in the hydrogen atom, should be trivial. And I'm just trying to argue that explicitly by looking at how flipping X, Y, and Z affect the spherical harmonics. But I'm getting a sign problem, which is not good. So this is, okay. Sorry, I'm not seeing the right thing, but it's taking too long. So let me, I'll comment on that on Friday, hopefully. So what I'm trying to say is that this representation, if you look at how Z2 acts on it, it should act trivially. No, sorry, it should act trivially here. We're tensoring by V1. And the problem is that this one, yeah, this one is excluded because of the fact that it's yeah, that's right. Actually, no, maybe what I did was right. So if I look at V1, this is the vector representation of SO3. So we have X, Y, and Z. It's just the usual three-dimensional space. The action of Z2 on this copy of V1 is just X, Y, Z goes to minus X, minus Y, minus Z. So it's obviously non-trivial on this V1. Now, when I tensor this with VL, the action of Z2 on this will be modified. So so you're going to get one, these two will have an opposite, these two will have a non-trivial action, whereas this one will have a trivial action of the Z2. And it's for this reason that this is excluded. So yeah, sorry, I'm not explaining this very well. So this action on Hilbert space excludes the VL summand, and we get only these possible decays. You have to go from the central from the column that you're in to the next column before or after. Yeah, sorry. Okay. I have two more comments that I need to make. So the next comment is that in solving the ODE, this ODE, there are solutions which are not in L2 in the sense that R multiplied by R is in L2. There are some solutions, and these can be described as plane waves for large r. So what I mean is that if you're trying to solve this system, what you could do to get an approximate solution is to let little r be very large, so that, and remember that the Laplacian looks like this. Okay, so basically, you can, if you want to get an approximate solution, you can let little r be very large, and then the dominant term here will be just this term here, and then this 2 over r, and this will combine, and so on, and then you'll get eigenstates of the Laplacian in one dimension, which are like waves, like e to the I. This is like e to the IR, IKR, something of this nature. Okay, and this means, so this means that we have approximate eigenvalues. Okay, so what do I mean by that? So imagine that you have this plane wave. So you have the proton is here, and then you have this wave function, which is a wave, and then something which we don't know what's happening here, but out away, very far away, it looks like a plane wave. So and these solutions have positive energy. All possible energies greater than 0. So the interpretation of this in physics is that these are scattering states. It basically means that it's possible that the electron is no longer bound to the proton, and that it has a positive energy. So it's basically scattering against the proton, or it's free to move in space. Okay, and the problem is that these states are so-called non-normalizable, which means that they're not in the Hilbert space. Okay, so from a mathematician's point of view, it's like saying, well, okay, that's a little odd. We have this self-adjoint operator. It's not bounded, as we discussed before. It's an unbounded self-adjoint operator. We found a bunch of eigenstates for it, but it appears that there are more solutions which are not in L2, not in the Hilbert space. So what's their interpretation? Well, one way to think about them is to cut them off at some point. So for a given radius, we could just multiply by a bump function that makes the solution, defined in the interior of this ball or this interval, and then 0 outside. Then it would be in L2. It would be in L2, and but the problem is that it wouldn't really be a solution. So it would not be an eigenstate. But if we apply the operator to it, the place where it fails to be an eigenstate is right in this area, the area where the bump is happening. Okay, and so what you can do is, and you can take a sequence where this bump is going farther and farther out. Okay, so we can produce a sequence of vectors in Hilbert space in math. We can multiply by bump functions and get a sequence in L2, a sequence psi sub k, such that the operator d psi k minus e psi k. So if I look at the this is the thing that should be 0 if it was an eigenstate, that this just approaches. as k goes to infinity, approaches 0. So it's an approximate eigenstate. And such a sequence is, well, this implies that E is not in the usual, is not an eigenvalue, but it's in the so-called continuous spectrum of the operator. So when you have self-adjoint operators which are unbounded, it can have this type of weird spectrum, which is that it's like a point which is not really in the spectrum. Actually, it is in the spectrum because we define the spectrum to include this. But it's in the spectrum not because it has an eigenstate in the Hilbert space, but because it has a sequence of approximating eigenstates. Okay, this is a new idea, and it's involved in the spectral theorem. You need to know this idea in order to understand the statement of the spectral theorem for self-adjoint operators which are not bounded. Okay, and the last thing I want to say is really important. That's why I'm annoyed that I have to go over when saying it. But the point is that in reality, the energy levels, because of the fact that the electron has a spin, and there are interactions between the spin and the proton and the electron, it means that the energy levels, which, remember that 2s and 2p, they were supposed to be degenerate. They were supposed to be exactly at the same energy. Okay, but it turns out that 2p has a slightly higher energy due to the spin orbit coupling, and you can make a higher and higher corrections. But the point is that experimentally, the p is slightly higher. That holds for all the p's. And then the 3D is slightly higher than the 3p, but it's approximately the same as the 4s, right? So there's a rule of thumb which the chemists use, which says that 1s is less than 2s, is less than 2p, is less than 3s, is less than 3p, is less than 3d. And then this is close to 4s. And then it continues with 4p, 5s, which is approximate to 4d, and so on. So basically the point is that they are not actually degenerate, okay? And well, okay, so what do we see? So imagine that you are imagine that you are building an atom, okay, and you start with a proton. Let's say you start with 50 protons. It doesn't matter. You put a huge positive charge. Then you drop an electron in. Where will it go? Well, it'll go right down here to 1s. Okay, and if there was one proton, then you'd be done. It would be neutral. Okay, so you would have hydrogen with one proton. Okay, now let's say you try to drop in another electron, because maybe there's more than one proton. Where will it go? Well, it could go up here, but actually there's more space here than you think, because this is not just a single state. This is always tensored with C2, because it has an internal spin state, the electron, which is two-dimensional. So that means that there's a two-dimensional space of states down here for the electron, not just one. Okay, so in fact, if we drop another electron in, it will also go down here. And then we'll get this helium 2. And then let's put another one in. Well, then where will this one go? It will not go down here, because this will be filled. We're going to talk about that more on Friday, because when I say that it's filled, I'm using the fact that electrons, when you have multi-particle states, when you have multi-particle states of electrons. So if you have a single electron, this will be in a vector space V of some, whatever that vector space is. And if we have two electrons, then it will not be in V tensor V, but rather it will be in the skew symmetric part of this. It will actually be in what they call wedge 2V, which is inside here, which are the skew symmetric ones, not the symmetric ones, but the skew symmetric ones. So these are like, for example, A tensor B minus B tensor A. Okay, and because of the fact that electrons behave this way, this is called fermionic. So a fermionic particle has this property that when you take multi-particle states, they're not just any random element inside the tensor product, but they have a constraint that they must be skew symmetric. And this basically says that this implies that you cannot put arbitrarily many electrons all in this same state. There's a maximum just given by these two. Just the fact that this is a two-dimensional space means that there's can only be two electrons. Okay, and then if you put another electron in, then it will jump to this level, and we're going to have another pair of elements which fill up these two pairs of states. What are they called? If anyone remembers. Lithium and beryllium. 3, and beryllium 4. So this one, and this one are all filling up these. So beryllium is the one that has the first two S states. They're again one-dimensional representations of SO3. One-dimensional representations of SO3. Okay, and then something interesting happens because all of these one-dimensional representations of SO3 are filled. And so then the next step is that I have a three-dimensional representation of SO3 available. And this three-dimensional representation counts for 6 electron states because I have spin up and spin down. So I have now all of a sudden 6 available states.
I don't think we can see what you're writing.
Oh, great.
Oh, there we go. Yeah, thanks.
Can you see what I'm writing now?
Yeah, I can see your cursor, at least your magnifying glass. Yeah, I can see it.
Yeah, it doesn't want to show me what I'm sharing. So wow. Okay, it's just right. So at this point here, there would be 6 available new states. So when you have your hydrogen and helium, and you have your lithium and beryllium, when you add an extra, then there will be 6 additional elements available at this point. And those are exactly these famous elements: boron, carbon, nitrogen, oxygen. What is this? Fluorine and neon. Okay, so the reason that there are 6 elements on the next row of the periodic table is because of P, the three-dimensional representation of SO3. That's why we have 6 here. Okay. And the same pattern will repeat again. If we go up again, we're going to have another 2 elements that fill up the 3s. Those are sodium and magnesium. And then you're going to have another 6 elements that fill up the 3p. And those are the aluminum, silicon, phosphor, what is it? P, phosphorus, sulfur, chlorine, and argon. Okay. And that's when something really interesting happens, because as soon as we get here, we're going to fill up the 4s. Remember that 4s is approximately the 3d, but we're going to fill up the 4s first. Potassium and calcium. Oh, potassium and calcium.
Or we don't see what you're writing again.
You don't see what I'm writing. Wow. Okay. Let me do this again on Friday. Sorry, I'm too frustrated. I just want to throw my computer out the window. I'm not going to continue. I'll continue on Friday. Sometimes it just doesn't work. Any questions? Okay, I have office hours. Right. Okay, we can work it out in office hours.